Good day, ladies and gentlemen. Today we're going to explore linear relationships lesson number 4. And in this lesson, we're going to talk about writing linear patterns from a table of values. In order to write a linear equation from a table of values, we're going to have to do similar steps as to what we saw in yesterday's lesson, which is going to require us to compute the rate of change or the slope, how much the relationship is increasing or decreasing by over and over again, what that repeated addition amount is. And we're also going to need to know the initial amount, where we started the relationship. Our objective is going to be to write linear relationships, the repeated addition patterns, from a table of values. The entire table of values is going to give us many data points, and what we know about yesterday's work is we actually only need 2 data points to write a linear relationship. So we're going to be given a lot more information than we need, and we're actually going to be rehearsing the exact same steps we saw yesterday. Please remember that repeated relationships or linear relationships are repeated addition patterns. They're the result of adding a constant amount over and over again. They have a constant rate of change, a constant amount of change. They're either increasing or decreasing by the same amount, and you should know that that's fine, because if they are repeated addition patterns, subtraction is just the same as adding the opposite. So we can still have a decreasing pattern where we're taking amounts away by adding the opposite. So it still follows the rule of what it means to be a linear or repeated addition pattern. Linear relationships will be known as first-degree polynomials. That's because the variable, often x, in other countries sometimes n, 90% of the time the x-axis is time, so we'll call it t a lot. That variable is going to be raised to the power of 1. And since we don't need to see the power when it's a 1, it's just going to look like the variable all by itself. That will change when we get to the power of 2 and the power of 3 and all different types of other nonlinear relationships as we move forward. The most common form or formula or presentation of a linear relationship is y, the measured amount, whatever it is we're investigating, is a result of a number of repeated multiplications of whatever the rate of change is. So m is the rate of change, the amount being repeatedly added over and over again, x number of times, plus the beginning amount b, wherever that pattern starts. In your calculator, you're going to see that relationship as ax plus b, which makes a lot more sense and is a lot more productive moving forward, because most of the other nonlinear polynomial relationships are going to refer to the first coefficient as a, the first numerical value, and the second as b, as these become more expansive expressions. So it's going to be important to understand that we use a and b and c and d variables more often than m and b. It's also possible to represent that as a decreasing relationship by putting the numerical constant first and subtracting away the rate of change times the number of times it's changing. We're going to see that quite often, and as we get to it, I'm going to show you why I like that as well. Linears may seem like multiplication, but please don't get caught up in that detail, because you're supposed to know that multiplication is just repeated addition. So there are students that will often say, Tooch, you told me that this was going to be a repeated addition pattern, but I'm looking at this and I see m times x. Isn't that multiplication? Yes, it is. Well, multiplication is just repeated addition. We've got to go back to some of the skills that we talked about in like 3rd grade. Because of the constant amount of change, the amount they're repeatedly adding over and over again, when we go to graph these relationships, they're going to make straight lines. That is not true for just about it's not true for every other relationship in mathematics. These are the only relationships that behave this way. So it's important that we know that. The constant amount of change is known as the slope and can be computed or observed in several different ways. Traditionally, the slope is known as the formula, the difference in y's over the difference in x's, where we're taking our final measured amount and subtracting out the beginning measured amount to see how much the measured amounts change, whether it's time or money or weight or anything else you could possibly be measuring. In the denominator, it's usually taking the difference in time. How much time did it take for that change to happen, for that amount of weight to be added, for that amount of money to increase or decrease in an account? How much was the unit of time? Was it 3 weeks? Was it 8 months? Was it 7 years? I don't know, but we'd have to figure that out. When you determine the change in y over change in x, you can simplify it. Some people call it the average rate of change, because triangle in the Greek symbolic system means change. And it's just a lot easier to write triangle y over triangle x rather than change in y over change in x. And graphically, we know this as rise over run. And since on a graph, the x-axis is the horizontal axis and the y-axis is the vertical axis, this technically means when we're rising, going up or down, we're describing the change in y. And when we're running, when we're going left to right, we're describing the change in x. So all 3 forms or formulas of computing slope are equivalent to one another. They're just different presentations for when you might be creating a linear relationship in different spaces or depending upon the information you've been given. Take a look at the worksheet for today, equation of a line from a function table. And I'm going to get you started on some of the do now work real quick to remind you of where we've been. And in Roman numeral 1, you're asked to identify the slope m, the rate of change, the amount being repeatedly added over and over again, or multiplied by x. Multiplication is just repeated addition. And b, the y-intercept, the value of the relationship at time 0, which technically means if you were to substitute 0 in place of x, y would equal 0 minus 1. Well, what's 0 minus 1? That's just negative 1. Y would equal negative 1 at time 0. So the y-intercept is telling us the value at time 0, or the beginning amount. That's why we sometimes call it b in that situation when we say y equals mx plus b. If you take a look at number 4, ladies and gentlemen, I'm going to jump right there. The number of Tickle Me Elmos sold on Black Friday per hour plus online orders. So every year there's like this really hot item that every kid has to have. And parents go nuts. They run out to the stores and they wait on lines forever when they find out that there's somewhere and there's a stock coming out at 6 in the morning. So they'll get online at 2 in the morning so they can get their kid that item. For a while, it was this Tickle Me Elmo doll. It's really stinking creepy. Get your hands on it. It tickles it laughs in such a weird way that if you were to be home alone and hear it, you would definitely think you're being possessed. Tickling Me Elmos on Black Friday, typically in the past, were selling at a very high rate. If you take a look at this relationship, I know it's linear because it's h to the first power. Because I don't see a power, I know it's to the power 1. So this must be a repeated addition pattern. Since it's a repeated addition pattern, it would be a good idea to write y equals mx plus b across the top. And that would allow me to understand that the amount of Elmos, the thing we're measuring, the y variable, is a result of 25 more each hour starting at 200. So maybe there's 200 that was in pre-sales. Before the people even walked in the door, they're already ready to go. They're just going to have to pick it up when they walk in. My rate of change, m, is that there's an additional 25 Elmos going every hour. My beginning amount, b, the amount that was done in pre-orders, is 200 that we have to put aside right away out of our stock because those people have already ordered. And that would be an opportunity to identify the rate of change, m, the amount being repeatedly added, and the beginning amount, b, in that real-life linear relationship. When you take a look at Roman numeral 2, it's asking you to take the slope determine. In Roman numeral 2, we're asked to determine the slope-intercept equation. So that just means the linear pattern in y equals mx plus b form. That's not the only form of formula, it's just the most popular one, of each line given the information. So again, I'll go to number 8. In number 8, we're asked to write a linear relationship describing the amount of candy needed to give out to trick-or-treaters with several pieces put aside for family per hour. So this is pretty cool because Halloween's coming up, so I often have written these questions in and around the time of what's happening in the world around us, or where our calendar is. And we get those big candy bars at my house. We're that house that gets the big ones that the kids love, and they like go around the corner and they switch their hat with their friend's hat, and they come back like they changed their costume because they want another one. It's a pain in the butt. But I always try and predict each year about how much candy I'm going to go through. I'm not predicting a lot this year for obvious reasons. But typically, I predict about 15 candy bars per hour. And I always get extra for my nieces and nephews because they always stop by, so I always get like 22 extra. I add up how many nieces and nephews I have, and I put those aside. And that allows me to predict how much candy I need to buy for Halloween. It's funny because Halloween's on a Saturday this year, and I will predict more. Because actually, I'll probably end up getting about the same. Because the day's longer, and typically I would need more, but because of Corona, less kids are probably going to come around. So I'll probably get the same amount of candy that I would have gotten on a weekday when kids would start trick-or-treating at, say, 4 or 5 o'clock and only go for a few hours. Based on the information we have, the rate of candy is going out of my house at a predicted amount of 15 per hour, and I'm starting at 22 that I put aside for my nieces and nephews. So if you think of this as a repeated addition pattern, you could say, Tooch, isn't one of the most popular forms of formula slope-intercept form, y equals mx plus b? And couldn't I substitute in that we are going to need 15 bars of candy every X number of hours starting at 22? And wouldn't it be appropriate if I wanted to use some more real-world variables to write this in a way that makes more sense, replace X and Y, so that I can actually interpret the relationship a little more easily? Why don't we call it C for candy? That's what we're really measuring. And why don't we say that we're going to start off at 22 and add an additional 15 every either T for time or H for hour? And that's just a little easier to interpret. That's a more interpretive presentation. If you go back to the previous one, please notice that I used the commutative property of addition to switch 22 and 15x. We're allowed to add in any order we want within an expression. We will not change the value of the expression. Cool. Take a look at number 10, and the instructions for number 3 say use your knowledge of linear equations to help write the equation for a line given the slope and 1 point. Remember, you must have the slope m, the rate of change, as well as the y-intercept b, the beginning amount divided times 0, to write the equation of a linear or repeated addition pattern. So when we write a repeated addition pattern, we need to know where that pattern's starting before we have any repeated additions at all. That's times 0. And we also need to know what the rate of change is. So I'll go with number 10 again. Write a linear equation function for the amount of money Brittany earned waiting tables if she got paid at a constant rate, and after 3 hours, she earned $58 total. We can represent that as the coordinate point 3 comma 58. That's x comma y. You might want to call it x1, y1. And after 7 hours, she earned $102. So I'm going to call that x2, y2. That's the second time I'm observing how long she's worked and the amount of money she's made at that time. So right away, the way I always begin this is if I want to write a linear relationship, I'm going to start with y equals mx plus b. If you know a formula, let's write it. And I'm going to recall that the two most important variables to describe this relationship, this repeated addition pattern, are m, what's being added over and over again, and b, the initial amount. M is going to have to be determined first. That's the rate of change. I need to know what I'm adding over and over again, and that's y2 minus y1 over x2 minus x1. That is one of the most popular formulas for the rate of change. It's going to allow me to actually compute it given some information. Since I already labeled my points x1, y1, x2, y2, I can substitute into that appropriately. Substitute using parentheses, and I like to kind of set the formula up even before I get started. So I'm going to do parentheses minus parentheses over parentheses minus parentheses. And I'm going to begin by substituting y2, the final measured amount, in the first position in the numerator. Then I'm going to substitute y1 in the second position. I'll continue to substitute the final time we measured after 7 hours of working, and I'll subtract out the first time we measured, 3 hours of work. And then I will simplify the expression. 102 less 58, I believe that is going to be 44. And 7 less 3 is going to be 4. So she's making $44 over 4 hours. Or another way of saying that, if we simplify further, is she's making $11 per hour. Once we know M, the amount she's making per hour, we might want to know what she starts at. So in a lot of restaurant jobs, you actually get like a shift pay. So long as you show up to work, you're going to make a certain amount of money. Often they send you home early if the restaurant's not so busy, but at least you'll get your shift pay for cleaning up, for getting your clothes on, for getting in your car, for taking the time to get to work. So at least you'll have earned that the beginning amount. So we need to determine the beginning amount. We're going to rewrite our form of formula y equals mx plus b. That's what's going to help us solve for b. And in order to solve for b, we're going to need to substitute in for y, m, and x. It doesn't matter which point in time and measured amount you use. Just make sure you're consistent. So if you choose 3 hours, $58, make sure that you understand that 58 is the total amount at that time. If you're not sure where to start, and you have it, start with the total. And she's earning $11 per hour for 3 hours, starting at B. So $58 is a result of her earning an additional $33 plus what she began at, what her shift pay was. So let's subtract out her additional earnings, and we can find out what her shift pay was, what she started at. Subtract out 33, subtract out 33, we're going to end up 25 equals B. Now that we know the beginning amount, and we know her rate of change, we can write an appropriate repeat addition pattern. Y equals $11 per X each hour of work, each time she works an hour, starting at 25. And I would encourage you to try and determine real-world variables in the context of the question, based on the question, that describe this a little more clearly. So we're talking about Brittany, and we're talking about her earnings. I like E for earnings, or maybe B for Brittany. And it's all happening based on time and hours, so maybe T or H. So there's a couple of different ways you could present this that would be more easy to interpret based on the context of the question. You could say Brittany is going to have $25 that she gets for her shift pay plus an additional $11 per hour. Or maybe you want to say E, her earnings are equal to starting at 25 and increasing by 11 every T number of times. And you can switch those around. Whatever you feel is the easiest to interpret is fine by me, so long as you understand it. Cool. Ladies and gentlemen, please take a moment and complete Roman numeral 1, where you're asked to identify M and B, the rate of change, the amount being repeatedly added, and the y-intercept. You should have M equals, you should have B equals for each of those questions. For Roman numeral 2, please take the slope and intercept, and in slope intercept form, y equals mx plus b. Please write an appropriate equation to describe the information you've been given. And in Roman numeral 3, see if you can use the model problem of Brittany and her earnings to take a relationship that has a rate of change of 4 and at time 1 measures 6 to write an appropriate linear pattern. Please change the rate of change to 4 in your workspace, and then go right ahead and substitute in for y, m, and x, and see if you can solve for b, and then write the appropriate equation below. Pause the video, give it a shot. Awesome. Hopefully your work looks like mine, and if your work looks like mine, ladies and gentlemen, and number 1, if you're identifying the rate of change and the slope, I hope you understand that there is 1x, therefore the rate of change is 1 over 1. It's going up 1 measured amount every 1 unit of time. We like to write the rate of change as a fraction. That way when we go to graph it, we'll already know what rise over run are. You're not wrong if you wrote m equals 1, but this is going to be more interpretive as we move forward. Same thing with b. You're not wrong if you wrote b equals -1 to value this relationship at time 0 would equal -1. But it's going to help you when we go to graph next week if you write it as 0, -1. If you understand that if if x were actually 0, then we would have 0 minus 1, which would in fact equal -1. When x is 0, the expression is going to equal -1. In number 2, everybody, if you're writing y equals mx plus b across the top of the relationship, I hope you recognize that m is -2/3. We're decreasing by 2/3 over and over again x number of times, and we're starting at time 0 with a measured amount of 9. Number 3 is a little bit funky because there is no x variable. That means there is no change happening whatsoever. And at right now, time 0, the relationship equals -7. And here's a little bit of a clue. It always equals -7 because there's no change. This is going to be known as a constant function. When we go to graph it, it's always going to equal a horizontal line. It's not going to go up or down at all. It's just going to stay the same. In number 5, you should have 5x plus 0 given a slope of 5 and a y-intercept of 0, 0, or perhaps just 5x. In number 6, you should have 1/2 x plus 1. And number 7 should be y equals 0x plus 7. Or if you prefer, anything times 0 is just 0, just y equals 7. Here's that constant function again. There is no rate of change. Therefore, when we go to graph it, it's just going to be a horizontal line. Down below, if you're substituting in for y, m, and x to solve for b, you should have the measured amount is 6 at time 1. So we're substituting 6 in place of y. That is the total 1 unit of time from now. The rate of change is 4. The amount of times that we're adding 4 is 1 time. 1 times 4 is 4. And if you subtract 4 away from the beginning amount, you'll learn this relationship starts at 2. And we're adding 4 over and over again. So y equals 4x plus 2. Or if you prefer, you could use the commutative property and write y equals 2 plus 4x. Hey, check this out. If at 1 unit of time from now it measures 6, couldn't we continue this pattern and go to 2 units of time from now by simply adding 4 and finding out or predicting that 2 units of time from now is going to equal 10? And couldn't we go backwards in time and undo addition with subtraction and determine that if we subtract 4 away, we're going to arrive at a measured amount of 2, and if we subtract 1 unit of time, we're going to arrive at 0. The rate of change is 4 over 1. We're adding 4 every 1 unit of time, so you could reverse that. You could subtract 4 1 unit of time, and informally, you could determine that at time 0 it measures 2. So we're going to see a little bit of that today. Cool. That brings us to today's work. And in today's work, ladies and gentlemen, we're simply going to take a table of values, and we're going to try and make a linear relationship from it. And the most important thing to recognize is that we just spent time yesterday talking about how you can make a linear relationship from 2 points. So we said if anybody gave you 2 data points representing a repeated addition pattern, you could find the rate of change and you could find the beginning amount. So technically, when you look at these tables, you don't need to look at the whole table. If you wanted to, you could really just extract out the first 2 points and say, hey, isn't it saying that 2 units of time ago it measured -5? And isn't it further saying that 1 unit of time ago it measured -3? And can I label those points x1, y1, and x2, y2? And can I go through the whole process or the same process we went through yesterday to find the relationship? You can. But it's actually easier in a table of values. Here's why. In a table of values, you can employ that other form or presentation of the rate of change, which is just triangle y over triangle x, changing y over changing x. And you can simply look as the table goes down, reading it as it progresses down your page, you can see what's happening. So if I see what's happening in the y variable, the measured amounts went from -5 up to -3. That's an increase of 2. And that happened in the units of time that went from 2 moments of time ago to 1 moment of time ago. That's an increase of 1. You can check it throughout the table. It should be consistent, or it should be proportionately the same. And you notice that the units of time are being measured every 1 hour, every 1 second, every 1 week, whatever. And the measured amounts are also constantly going up by 2. So the rate of change clearly has to be 2 over 1. The rate of change is an increase of 2 measured amounts, change in y, over every 1 unit of time. Now, you could have used the slope formula from yesterday. You could have said, Tooch, wasn't I supposed to do y2 minus y1 over x? You can. You can do whatever you want, as long as you do it mathematically correct. That's just going to be a lot more work than observing it throughout the table as a change in y over change in x. Once you know n, you got to go back and get b. And in order to get b, you're going to need to rewrite a form or formula that's familiar to you. Hopefully, y equals mx plus b is the most common form that most of us use, and you'll use it often as well. And in y equals mx plus b, our linear relationship slope-intercept form or formula, I often substitute in the first point, just because it's there and it's often easiest. And in some instances, it won't be. Technically, you can substitute any point in the pattern. But I'm going to say that this relationship measures -5. That's the y variable amount. As a result, or because it's going up 2 at a time, and it measured -5 2 moments of time ago, plus b. And if I solve for b, I find out that if I subtracted 2 twice, I must have subtracted 4 from the beginning amount. And the result was it measured -5. And I'll add that 4 that must have been subtracted back into the relationship, and I'll find out that 1 moment of time ago it actually must have equaled -1. I'm sorry, at time 0 it must equal -1. So now that I have my beginning amount, this relationship must have started at -1, I can go ahead and take that along with the rate of change and write a repeated addition pattern. Y equals 2x minus 1. Or if you prefer, you can say y is starting at -1 and we're adding 2 over and over again x number of times. Hey, what's really neat about that is I kind of created this question on purpose to actually have the data for you in the table. You could have just observed the beginning amount. It's right there, 0, -1. I did that on purpose just to prove that it works. So when we computed the beginning amount, it's matching what I had already given you. Often tables won't have the beginning amount in it, the value times 0, but it was right there. Hey, Tooch, if that's the case, couldn't we have just extracted it right out of the table and written the equation right away? Yes, technically you could have. Ladies and gentlemen, please jump to the back end. On the back, I would like to do a couple more of these problems together, and I'm going to have you do a couple on your own to make sure you truly get the concept. When we work with tables of values to describe linear relationships, we know that we simply need to determine m and b to describe a linear relationship, the mapping repeatedly added in the beginning amount. When you do that with data points, technically you only need 2. So you're not wrong if you're like, Tooch, can I just focus on the first 2? Can I extract those 2 points out and write them as coordinate pairs as if I were preparing to graph them and say that 3 moments of time ago this relationship measured 9, I'm going to call that x1, y1. And 2 moments of time ago, this relationship measured 7, and I'm going to call that x2, y2, and I'm going to do what we did yesterday, which is use the slope formula, changing y over changing x, and I'm going to compute it. You can do that, but here's what I'm going to recommend. Another way to determine the slope is to consider the change in y over change in x, and you can kind of just observe it rather than compute it. You can look and see what's happening as your eye observes the pattern going down the table. And I notice in this instance that my measured amounts are going from 9 down to 7, so that's a decrease of 2. All right, that's a little weird. Let's just check that out again. 7 down to 5, that's a decrease of 2. 5 down to 3, that's a decrease of 2. 3 down to 1, that's a decrease of 2. You don't need to check all of the changes throughout the table, but I just did to make sure that things were happening correctly. For the x variable, the units of time went from 3 moments of time ago to 2 moments of time ago. That's an increase of 1. From 2 moments of time ago to 1 moment of time ago, increase of 1. And you'll find out that the relationship is decreasing 2 measured amounts every 1 unit of time. And by observing that, the rate of change is simply -2 over 1, exactly what you get if you use the slope-intercept formula, y2 minus y1 over x2 minus x1. It's just much more efficient. Once I know the rate of change, the only thing I need to determine beyond that is what the beginning amount is. Hey, wait a minute, Tooch, you tricked us once before on this. For this particular question, do we have to find out the beginning amount, the value times 0, or isn't it just right there in the table? Isn't it going to measure 3 at times 0 because it says that? It is, but this time let's actually prove it. Since you're so smart and you made that observation. B is 3. M is -2. And this relationship will be y equals -2x plus 3, or if you prefer, start at 3 and subtract 2x number of times over and over again. That's why the relationship is decreasing. But let's take a look. To solve for b, I often use the first point in the table. You could use any point in the table, technically. It'll work. I suppose I'll use this one here. I'll use the last one just to prove it. So if I use the last one, ladies and gentlemen, and I want to say that the relationship measures one unit of time from now, I would substitute 1 in for y as the measured amount. I would substitute the rate of change as -2. We just computed it or observed it. I would say that it's measuring 1 as a result of going down to 1 time, starting at b. As I solve this equation, I would simplify the expression on the right. -2 times 1 is -2 plus b equals 1. And I'd have to add 2 to both expressions to solve for b. I find out that b is in fact 3. Typically, you would have to go through that step because you're not going to be given the initial amount in the table of values. But if you are, you don't have to. Cool. Jump down and let's take a look at number 15 together. And in number 15, we've got a table of values describing water in gallons. And we're measuring that water throughout time in hours. We notice that it is increasing. You're told that it's a linear relationship because that's the title of the entire worksheet. So it would be a good idea to begin by writing, or suggesting that if we're writing a linear relationship, one of the most popular forms of formulas is y equals mx plus b. And the two most important variables are m, the rate of change, and b, the beginning amount. As we try to determine what m and b are, you're not wrong if you say that m is y2 minus y1 over x2 minus x1. You've got to compute the difference in measured amounts over the difference in time to figure out how it's changing. But it's much more efficient to say that m is simply going to be the change in y over the triangle or change in x. And in order to determine that, we could see that the pool water is being observed or measured every 3 hours. And what we're determining, or what we're observing, is that every 3 hours, it is going up by what appears to be 60 gallons. Increase of 60, increase of 60. Technically, you only need to observe the change in the first two because you're told that it's linear. Later on, when we see tables that aren't linear, you're going to have to figure out, is it going up by a constant rate or is something else happening? So because it's linear, technically all you need to do is to check out the difference between the first two measured times and determine that we're measuring in 3 hours and having an increase of 60 gallons, and you can write your rate of change as a 60-gallon increase over every 3 hours. If you want to simplify that, 3 divides into 60 20 times. So apparently this is going up 20 gallons per hour. Once we know n, we got to go back and find b. And in order to find b, it's going to be important to rewrite our formula. This is not the only form of formula, it's just the most popular one, slope-intercept form. And we're going to have to substitute appropriately. Substituting into slope-intercept form, we're going to have to take some point in the table. I often work with the first point, and I'm going to suggest that this relationship is measuring 140 gallons as a result of increasing 20 gallons for 3 hours, plus the beginning amount. And I end up with 140 equals 60 plus b. From there, if I were to subtract out the 60 gallons of increase over those 3 hours, I'll find out that there was 80 gallons in the pool to begin with. So this is kind of neat because, especially for my family, we got one of those little inflatable pools this year. I can't afford those big giant ones. God bless you guys if you have an in-ground pool. Man, that was an awkward summer. It started off really hot. But we have to fill it up, and sometimes I have to take the water out and clean it and brush it and all that jazz, or put some more chlorine and what have you. And you can imagine that after one cleaning, maybe there was still 80 gallons of water. And then when I went to fill it up, I was filling it up at a rate of 20 gallons per hour plus the initial 80. And if you want to write that in a more interpretive presentation, you might choose to call we're measuring g instead of y, and you might choose to call x h instead of the x variable itself. 90% of the time, the x-axis time anyway. So a more interpretive presentation of this may have been, why don't we say that the number of gallons is a result of starting at 80 that's left in my pool, and it's going to increase by 20 every h number of hours. That would be a more interpretive presentation. And then based on this function rule, function just means useful equation, we'll talk about that later on. Based on the useful equation, at this rate, how many gallons of water would there be after one whole day, 24 hours? So after 24 hours, we simply need to substitute 24 in place of h or in place of x, depending upon which equation you choose to use. So I'll use the second one. Gallons is going to be a result of 80 increased by 20, 24 times. And gallons is going to be a result, you can just type that whole expression into your calculator, but I'll simplify it, each term. 80 is going to be a result of, I believe that is, I'm still going to get this wrong, 480 gallons. And that would mean that the total number of gallons after a full day is 560. Cool. Let me take a moment to get you started on number 13 and 14, then you can try to finish them on your own and see if you truly understand the concept. So number 13, in this linear pattern, if you're looking to write the equation of a line, you should start by computing m. The easiest way to do it when you give it a table of values is observe the rate of change, and we should know that y is going up 2 measured amounts every 8 units of time. I'll just check to make sure that's true. 2 measured amounts, sorry, every 8 units of time. 9 to 11 is an increase of 2 measured amounts, and 12 to 20 is an increase of 8 units of time. So the rate of change for this one's a little bit tricky. It's it's going up 2 measured amounts every 8 units of time, or that simplifies to 1/4. See if you can figure out how to determine b by substituting into y equals mx plus b for y, m, and x. And if you're able to solve for b on your own, see if you can write out the appropriate repeated addition pattern. For number 14, ladies and gentlemen, in order to write an appropriate linear relationship or repeated addition pattern, we often like to present them in slope-intercept form, y equals mx plus b. Two most important variables are m and b. M is just the change in y over change in x. And you can observe that in a table of values. The plant appears to be going up 1 inch every 2 days. 1 inch every 2 days. That appears to be consistent. Technically, you only need to figure out the first change in a linear pattern, but I just wanted to make sure that things were happening proportionately the same. So our rate of change should be 1 inch every 2 days. Now that you've got M, I need you to try to solve for B, the beginning amount. The beginning amount of this relationship is going to be a result of taking y equals mx plus b, the most popular form or formula of a linear relationship, and substituting in for y, m, and x to solve for b. It doesn't matter which point you choose from the table. I often choose the first one to substitute in for my y, x variable, along with the rate of change 1/2, and solve for b. Once you're able to do that, please write an appropriate linear equation to describe this repeated addition pattern. Start with y equals, and then try and do one where you are changing the variables to something more appropriate for this particular relationship. Please pause the video and try and finish 13 and 14 on your own. Okay, let's see how you did. I left you with having determined the rate of change, which was 1/4 for this repeated addition pattern. It was increasing by 2 measured amounts every 8 units of time. And from there, you're supposed to rewrite the formula for a linear pattern, the most popular form of formula, slope-intercept form, y equals mx plus b. You'd have to substitute in for y, m, and x to solve for b. I chose the first point, -4, 5, so I said that this relationship is going to measure 5, 4 moments of time ago, having gone up a quarter over and over again. So if I multiply 1/4 times -4, I take a quarter of -4. You got to do that on your calculator, or no denominator means divide. 4 divides into -4, -1 time, and -1 times 1 is -1. You can then solve for b by adding 1 back into each of the expressions, and you find out b equals 6. At time 0, this relationship equals 6, and therefore we can describe it as y equals 1/4 x plus 6, or if you prefer, start at 6 and add, oops, that's a mistake, 1/4 over and over again, x number of times, or add a quarter over and over again. For number 14, I left you off having considered that the plant is increasing at a rate of 1/2 inch per day, or another way of saying that is 1 inch every 2 days. And once you had M, you had to go back and get B. In order to get B, you have to substitute in for Y, M, and X. It doesn't matter which point in the table you select. I often choose the first one. I chose to describe this as a measured amount of -2, that's my total, at time 2, as a result of going up 1/2 inch per day. So I substitute in for Y, M, and X. I evaluate, or I simplify 1/2 of 2, which is just 1. The plant has gone up 1 inch after 2 days. It has increased by 1 inch, so I'm going to subtract that 1 inch out, and I find out that the beginning amount was -3, which to me would suggest the plant was planted 3 inches in the ground and is increasing at 1/2 inch per day. Y equals 1/2 x minus 3, or if you prefer, the height of the plant using a more appropriate or interpretive variable is equal to, or has started at -3 and is going up by 1/2 inch every day. This is the lesson on being able to write a linear pattern from a table of values, and writing a linear pattern from a table of values is really kind of easy because it goes back to what you saw in the previous lesson, where you simply have to focus on 2 particular data points to find a linear relationship. 2 particular data points is going to allow you to determine the rate of change, and you can do that informally in a table of values by just observing it as the change in y over change in x. Once you find the rate of change m, you need to find the next most descriptive variable within a linear relationship, which is the beginning amount. How much does it measure at time 0? Often that requires you to take a formula, like slope-intercept form, and substitute in for y, m, and x to solve for b. Sometimes it'll be given to you in a table. In this instance, it was not. And if it is, then the work is a little bit easier. I hope you understand the concept, and I will see you in class. Be well.